Hi, in this video we will be looking at some of the foundations of trig, some of the vocab words, and some of the stuff that you're going to be working with throughout our studies of trigonometry, and that follows with section 4.1 from our textbook. So to start off, when we talk about angles, you need to know that we always put angles in standard position unless we're told otherwise. So since we work so much with standard position, you need to know what standard position is. So an angle is in standard position if its vertex is at the origin. So think of this like the x-axis and the y-axis. So the origin would be right there in the middle. And one ray is on the positive x-axis. So positive x is right there. So that side is what we're going to call the initial side. So the side on the positive x-axis. Okay, and then then the angle turns and opens up. So this would be like the angle. We usually use the Greek letter theta for that. And if you're talking about a small angle, it's not going to open up very much. Bigger angle is going to open up more. But to have an angle, you need another ray. So the terminal side is going to be the other side. So it's the one that's going to move around depending on how big the angle is. Now you can have positive angles and you can have negative angles. Positive angles are angles that start on the initial side and rotate in the counterclockwise direction. So a couple of examples of that would be like from positive x, if we went opposite a clock, counterclockwise, 30 degrees, this is what positive 30 degrees could look like. Starting on the positive x-axis, if I opened up 80 degrees, positive 80 would be counterclockwise. So 80 degrees would look something like that. Okay, so the important thing is the direction here. From here, turning this way. From here, turning this way. So a negative angle is just an angle that measures in the opposite direction, so in the clockwise direction. So I'm going to use these same numbers. If 30 degrees opens up that much that direction, then negative 30 degrees would open up the same amount just in the clockwise direction. And 80 degrees, how much it opens up counterclockwise is the same amount that it would open up just counterclockwise. Okay, so whether the angle's positive or negative, all that's going to change is the direction that you're measuring. Alright, so you should have quite a bit of experience with degrees, but radians you may not, or actually you probably do have a tiny bit that you don't really realize, but you will need to know the difference between a degree and a radian to get going in trigonometry. So in degrees, let's cut these circles up. In degrees, you know that like if you didn't open up an angle at all, you would have 0 degrees. And you know that a right angle is 90 degrees. So if you did another one of those, that's 180 degrees. You could maybe find what's in the middle of 90 and 180 to find what's in the middle here. And of course you could keep going and you go all the way around. We know all the way around a circle is also 360 degrees. So you can find all kinds of angles in there. This one's 270. But the main thing I want you to focus on, because there's really only one thing you have to know to be able to begin to work with these. If you know a circle all the way around is 360, but in radians, so you could either open up not at all, which would be 0 radians, or if you went all the way around, that's 2 pi radians. Make sure that you know that. Make sure that you've memorized that. Because with this fact, you can figure out where a lot of the other angles are. So just like 180 is half of 360, half of pi over 2 would be 1 pi. I'm sorry, half of 2 pi would be 1 pi. In between 180 and 360 was 270, and in between 1 pi and 2 pi would be 1.5 pi. But we like to write that as a fraction. In the middle of 0 and 180 was 90. In the middle of 0 and 1 pi would be half a pi. And you can keep going. You got to think a little more in fraction terms here. But between a half and 1 would be, in the middle would be 3/4. And so you can figure out a lot of radian angles that you need to work with like that. Now actually in the next section, we will really dive deep into the unit circle. And in the unit circle, you have to memorize a lot of these values and where these angles are anyway. But this is just kind of a tool to kind of help you see how they compare. 135 degrees is the same thing as 3 pi over 4 radians. Now notice I didn't write radians on all these. Radians are considered a blank unit, so if you don't put any units, it's assumed to be radians. So you can say pi over 2 radians, or you can just say pi over 2. I tend to just say pi over 2 because it's a little bit easier. Alright, so we'd like to be able to convert from degrees to radians, and then from radians to degrees. Since you're more familiar with degrees, this is kind of a good tool for you to have early in the semester, because it helps you maybe convert a problem that you're less comfortable with to degrees, and then maybe it makes you feel a little more comfortable, and then you can convert it back later on. Well, converting these, it's just like any type of conversion. So like if I had 3 inches, if I wanted to convert that to feet, I would multiply by its unit conversion. So I could say something like 12 inches is the same thing as 1 foot. Now notice, I want these inches to go away, so if I have inch units in the numerator, I would want to put my inch units in the denominator, and then I would get 3/12 feet, and then of course we would reduce that to 1/4 of a foot. So this is just like how you would convert from inches to feet. Well, there's a unit conversion to change from degrees to radians. So if I have 120 degrees, just like I wanted these units to cancel out, I really want this degree unit to cancel out. Because if I'm just ignoring it, that's probably not working out for me. So the magic conversion that most people use is they say that 180 degrees is the same thing as pi radians. 180 degrees is the same thing as pi radians. Now notice these have to be equal, right? If you multiply by something, if you multiply by 2, you change the size. If you multiply by 1, you don't change the size. So anything divided by itself is 1. So here I multiplied by 1, so here I'm multiplying by 1. These are equal in size. And that's important because I'm changing the way it looks, but I'm not changing its value. I'm not changing how big it is. Okay, so then I could say that comes out to be 120 pi over 180, and then we need to reduce that. So I could divide both by 10. I could divide both by 6. Yep. So you do have to reduce it. And it looks like 120 degrees is 2 pi thirds radians. Now, see, I actually know that because I know the unit circle very well, and in a week or two, this is one you probably wouldn't use this little conversion for, but sometimes it's necessary. So while we have these circles up here, let's go ahead and see that that makes sense. So if we said half a turn is pi, imagine cutting that up into thirds. So this is about where 1/3 pi is. Add that amount again to get to 2/3 pi. Add that amount again to get to 3/3 pi, which of course reduces to 1. So I'm saying it lands right here, and over here we can see 90 and 135. It's going to be in the same spot. So my unit conversion, I can visually see that checks out. Okay, so let's do another one. If I wanted to convert 50 degrees to radians. Okay, so the only time I see students struggle here is occasionally they'll do, they'll switch up which one's on top. They'll say 180 over pi or pi over 180. They have a hard time remembering which is which. So this is why I'm really going to emphasize to you, you want degrees to go away. So degree units in the numerator would cancel out degree units in the denominator. So that's how I know the 180 is in the denominator and not in the numerator. So multiply my fractions, multiply across the top, multiply across the bottom, and reduce. Both of those divide by 10. So 50 degrees is the same thing as 5 pi 18ths in radians. Okay, so again, it's not really any harder than converting from inches to feet or feet to inches. It's just a little bit different. You're just not used to working with pi quite as much. You haven't thought of radians as long as you thought about inches and feet, but it's the same thing mathematically. Same logic. Alright, so to switch to radians to degrees, we're just going to do the opposite. I'm going to take my radians and I'm going to multiply by something to make this go away. Well, I want this to become degrees, and I want to imagine dividing out these radian units. So in this case, I'm going to put the 180 degrees on top and the pi radians on bottom, which is the complete reciprocal to that. So that's why you've got to know which one you're doing and you're not just guessing. Then if I multiply across the top, I get 180 pi degrees over 3 pi. And if we reduce that, oops, let me skip this over. If I reduce that, the pi's reduce, and 3 goes into 180 60 times, 60 degrees. Now you do have to make sure that if your answer is 60 degrees, you have to use the word degrees, you have to use the symbol, one of the two. But if you didn't put either, by default this means radians, and that's something completely different, so that would be wrong. So make sure that you get in the habit of saying degrees if it's degrees. If it's radians, you can leave it blank if you want to. Alright, for 5 pi over 6, I will multiply by 180 degrees over pi radians. So this time I'm going to, not cheat, but I'm going to do some of the reducing before I multiply. Pi divided by pi, those cancel out or go to 1. This goes into this 30 times. So I'm left with 5 times 30 on top and a 1 on bottom. So 150 degrees. Now this is also one that you're going to use on the unit circle. So notice with my pictures here before we move on to another topic that visually this makes sense. Again, all these topics are foundation, so you're going to be using these and using these and using these for a long time. So the more connections that you see, the easier things are because you can kind of see them in different ways. But if I try to divide up this pi radians into 6 equal pieces, it's be like 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. So here's where 1, 2, 3, 4, 5. Here's where 5 pi over 6 is. Well, if I divided 180 degrees into 6 pieces, that would be 30 degrees. So 30, 60, 90, 120, 150, 180. So notice 150 lands in the same spot as 5 pi over 6. That's all we're doing here. Sometimes it's just too much work to always do a visual, so having this little unit conversion is a quick way to do that. But I hope that you can see how those two land in the same spot. Alright, our next vocab word here is coterminal angles. Coterminal angles are angles that have the same initial side and the same terminal side. So an example of that would be these two angles. So 330 degrees would start on the positive x-axis, and it would turn all the way around, which would be 360, but 30 less than that. So this much of a turn is what we would call 330 degrees. Okay, now if I did negative 30, remember negative angles are measured this way, so negative 30 looks like this. But notice these two angles, they both start at the same place and they both end at the same place, so the word for that is coterminal. They're not really the same angle. One opens up a lot, one barely opens up. But because they land in the same place for trigonometry, that ends up being really important for a lot of stuff that we do. So you'll have to just trust me with that for a week or two, but you'll see that knowing that those two land in the same place is helpful to us. Okay, so what would be an angle that's coterminal to 10 degrees? So if you would pause your video here and force yourself to make a guess there, and then unpause when you're ready. Alright, so what I could do is I could say, well, going 10 degrees this way is the same as going negative 350 degrees. There we go. The negative makes it turn the other way. So 10 degrees this way is the same thing as 350 degrees the other way. And what do you think? Do you think that there would be others? And the answer to that is yes. Because who says that you just go around once? Maybe I want to go around 2 times and then come around. So that number starts to look bigger, but as long as it starts and ends at the same place, then you get the same value. So I do want to make a connection to these here in a minute though. Notice 10 degrees, negative 350. There's some kind of connection between those. Okay, what would be a positive coterminal angle to negative 110, or negative 100? So negative 100 would look like this, approximately. So if I wanted a positive one, I could say, okay, I'll start here, and I'll figure out how much of a turn this is. Well, together they're 360, so turning 100 this way would have to be like turning 260 the other way, because then together they make 360, which is all the way around. Okay, what would be a negative coterminal angle to 60? So this is what 60 looks like. I do encourage you to try to draw these pictures too. The visual, after a while, I don't know that you need the visual all that often, but definitely early on with trigonometry, visualizing it helps you out a lot. Okay, so I could say, well, here's 60. Maybe I'll go all the way around again, which would be adding 360 to that, and that would be 420. But I want you to ask yourself, why would that not work as an answer here? So it is a coterminal angle, but for whatever reason this specific one just says give me a negative one. So maybe instead of going all the way around that direction, I will go around the other direction. So I will subtract a circle in the other direction. So that would be negative 300. Okay, so now let's start to look for a pattern here. If an angle has to start and end at the same place, what you're really doing here is you're adding or subtracting 360. Notice I subtracted 360, so I went all the way around the circle. I I added 360, which went all the way around the circle. I made sure these totaled up to 360, and in this case, I subtracted 360 because this is going all the way around the circle. So you might want to subtract 360 or subtract 360 a couple times if you specifically want a negative coterminal angle, and you might add 360 or add 360 multiple times if you wanted a positive coterminal angle. Okay, so this is the last one with degrees, and so please pause your video, try this as an example, and see what you get before I work it out for you. Alright, so hopefully you found two answers to this question because it wanted a positive and a negative coterminal angle to 150. So 150 is going to be about right here. But if you really thought about what I was saying about adding a revolution, adding 360, or subtracting a revolution, subtracting 360, you don't really need the picture anymore. To go this far and then to keep going, you would just add 360. So out to the side, I would say 510. So looks like what that totals up to be. Or I could go this way, which would be negative. And so I could subtract 360, which would end up being negative 210. Now, those aren't the only answers. If you want to add 360 more than one time, you can. If you want to subtract 360 more than one time, you can. But those are the first answers we get to, so most people just stop there because why would you make more work to get just an equally right answer? Okay, and so there's all that with degrees, but you also need to be able to do it with radians. Well, if you really understand this, and if you don't, I would recommend you back it up and watch it through it again. Feel a little more confident here. I was adding and subtracting 360 because I was talking about degrees. Well, if I'm talking about radians, I can add or subtract 2 pi, because remember, 2 pi radians is equivalent to 360 degrees. Okay, so let's work it out. What is 3 pi over 4 plus 2 pi? Alright, so for this you're going to have to review your fractions. Working with radians often makes you deal with fractions. So to add fractions, you need a common denominator. Okay, so I can rewrite 2 pi as 8 pi fourths, and then I can say 3 pi fourths plus 8 pi fourths would be 11 pi fourths. Okay, and then is there any others? Definitely. You could add 2 pi again. We could have subtracted 2 pi. There's infinitely many coterminal angles, depending on how many revolutions you want to go around. But if the question is just what is a coterminal angle, then I'm either just going to add 2 pi or subtract 2 pi and be done. I'm not going to make it harder than it has to be. Alright, moving on to complementary and supplementary angles. So these two terms should be familiar to you from your geometry courses. I'd also make sure that you are familiar with those terms for the ACT. So complementary angles is when you have two positive angles that add up to 90 degrees, and 90 degrees is the same thing as pi over 2 radians. So let's look at our picture up here from earlier. 90 degrees is the same thing as pi over 2 radians. Now remember, I kind of walked you through how you can reason through that until you have it memorized. So if I wanted to find a complementary angle with 85, I could probably do that pretty quickly in my head and say 75. I can do that very quickly. If I wanted to know what's complementary to 89, I could just say 1. But in a minute, when it's radians, it's not so easy for me to throw those answers out at you. So let's really slow down and think about what we're saying. We're saying, what angle plus 15 degrees gives me 90 degrees? Because they add up to 90 to be supplementary. Well, now I just got an equation. Subtract 15 degrees from both sides, and I get x is 75. All right, 91 degrees. Well, 91 degrees, you can do the same thing. What plus 91 gives you 90? And I guess you could get an answer of -1, but by definition they're supposed to be positive. So let's say not possible here, or no solution. All right, now it's really important to me that you think of it in this way, because radians, especially since you're not as familiar with radians, that's a lot harder to do. I can't just ask you what is the complement of pi over 3 and expect you to spit out an answer as quick as these two. But what I do expect is for you to say, this is saying what angle plus pi over 3 is pi over 2, because remember, complementary angles add up to pi over 2. Then you've got an equation that you can subtract pi over 3 from. And now our answer is right in there. We just need to get a common denominator and do that subtraction. So I could force them to have common denominators of 6. And 3 pi 6 minus 2 pi 6 would be 1 pi 6. Okay, so let me kind of backtrack. Remember we, just a few minutes ago, we did converting from degrees to radians. Now this is a very inefficient way, and I would not recommend that you do this very long term. But you can kind of do this as a crutch temporarily. If you wanted to change this to degrees, you would figure out this is the same thing as 60 degrees. Then you could ask yourself, well, what's the complement of 60 degrees? Which is much easier for you to do in your head, which is 30 degrees. And that's okay, but you do have to convert it back. 30 degrees is the same thing as pi over 6 radians. If a question is given to you in degrees, it's expected that you give your answer in degrees, unless the question says different. And if it's given in radians, it's expected to give you in radians. So that's just one rule, one way where the converting between degrees and radians and degrees can be helpful. You can kind of think of this in a different way. All right, so for this one, what angle could I add to pi over 9 to get pi over 2? And so I could subtract pi over 9 to the other side and get a common denominator. So that would be 18. Okay, and 9 pi 18ths minus 2 pi 18ths would be 7 pi 18ths. Okay, so as long as you understand why I'm setting it up the way I'm setting it up, it just gives you an equation to solve, and you've got to add or subtract fractions, but not too big a deal. Alright, this one looks differently, but it's really not that much different. Most of the time, 99% of the time, I'd say radians are going to be in terms of pi, but they don't have to be in terms of pi. So in fact, let me go back up here. Notice I was writing all of these in terms of pi. They had a pi in there. But 0 is not in terms of pi. Instead of saying pi here, I could have thought of this as about 3.14. So really, from about here to here, this is about 1 radian. Add that again. From here to here makes up 2 radians. From here to here makes up about 3 radians. So that when you get to here, it's about 3.14 radians, or pi radians. So radians, usually in terms of pi, but they don't have to be in terms of pi. Okay, and also, this doesn't even have to say radian. It could just say 1. You shouldn't assume that that means degrees because it doesn't say degrees. If it doesn't say the unit, you assume that it's radians. Okay, so I'm saying, what could I add to 1 radian to get pi over 2? Subtract your 1, and that's it. Those aren't like terms, you can't force them together. That's your answer. It feels different, but I approached it with the same logic, and you know, try not to overthink it, try not to do too much to it. Alright, so let's move on to supplementary angles. Supplementary angles are when you have two positive angles that add up to 180 degrees, and 180 degrees is the same thing as pi radians. Alright, so find find a supplementary angle with these degrees and those radians. And if you understand the logic behind the last couple questions that we did with complementary angles, you can do the same thing here. You just set it equal to pi instead of pi over 2. Or with degrees, you could say, what could I add to 80 degrees to get 180 degrees? And then you could solve that. Or what could I add to 120 degrees to get 180 degrees? And you could subtract 120 from both sides to get 60. And then you could do 210, and you'd get a negative angle, but by definition they're supposed to be positive, so not possible. And then if you switch from degrees to radians, the only difference, other than having to deal with fractions, is you can say what plus pi over 4 gives me, well, you have to know that 180 degrees is equivalent to pi radians. If this is in radians, you want that to be radians, and your answer needs to be in radians. So I could subtract pi over 4 from both sides, and then you could get a common denominator and subtract. You would end up with 3 pi over 4. Okay, so then what about 3 pi over 4? What could I add to 3 pi over 4 to get pi? And that would be 1 pi over 4. So these two make sense. If pi over 4, or if 3 pi over 4 is supplementary to pi over 4, then pi over 4 is supplementary to 3 pi over 4. It goes both directions. And then here's another one where radians are not in terms of pi, but I can still set it up the same way. What could I add to 2 radians to get pi radians? And the answer is pi minus 2. I know the temptation there, or there is a temptation there to type it in your calculator and get a decimal, but unless the question says to round, you really shouldn't want to do that, because this is an exact answer. So why would you do more work to get a less accurate answer? Just leave it exact unless you're told otherwise. Alright, moving on to degrees, minutes, and seconds, and how that compares to decimal degrees. So degrees, minutes, and seconds is a type of degree often used in real-world problems, so like airplane navigation, ship navigation, latitude, longitude, etc. So the way this works is you usually have like a set number of degrees, and we know the degree symbol. You have a set number of minutes, and then one little tick mark is for minutes, and then you may have seconds, which is just 2 little tick marks. Whereas where I say decimal degrees, it just means you have some degrees and it's got a decimal to it. So 44.125 or something like that. It's got some kind of decimal there. Okay, so you do need to convert back and forth between these when you're given problems that are ship navigation and airplane navigation, etc. If you're going to work with them, you probably need to change them to decimal degrees, because this is what we're used to looking at. Alright, so to convert from degrees, minutes, and seconds to decimal degrees, you could use a calculator in 2 different ways. And the first way is what I prefer. You can take the number of degrees, you can add the number of minutes divided by 60, because 1 minute is a 60th of a degree. Then you can add the number of seconds divided by 3600, and that's because there's 3600 seconds in an hour, and 1 second is 1/3600th of a degree. Okay, and then I can throw that in my calculator. So 60 full degrees plus 34 over 60 plus 54 over 3600. And put parentheses around my fractions. That ends up being about 60.582. And I had to round there. So these are saying degrees. These are basically saying the same thing, only basically because I had to round. But it might be written like this for latitude longitude problem, but I might want to convert it like this so I can have it as 1 degree. It's very close to 60 degrees, but to get that decimal right, we got to convert it. Alright, you can also type it in the calculator, and I'm not as big a fan with this because you have to know where to find the degree symbol and the minute symbol. But if you want to, you can search through your calculator to find the degree symbol, type in 34, find the minute symbol, and then find the second symbol, hit enter, and it will show you the same decimal that I got before. The only reason I'm not a fan of that is either you have to memorize something, like where those functions are in the calculator, and doing it this way it's a constant reminder, like what a minute is. A minute is 1/60th of a degree, and it's a constant reminder that a second is 1/3600th of a degree. So I think you have a little better understanding here, but technically your calculator can do it for you if you want to practice that. Alright. So to go in the other direction, you can do one of two things too, but by far the method that I prefer is to get your calculator to do it. So your calculator has an arrow DMS command, which basically means change to degrees, minutes, and seconds. So my calculator, I would do, that, and then I would find that command. Okay, I don't know how to type right now. And hit enter. And it's going to change it to degrees, minutes, and seconds for me. I will do that on my own personal calculator. Now, you also kind of have to know where the arrow DMS is, but if you hit second 0, it'll pull up the catalog, and then you go all the way down to D's. You should be doing this too. You need to make sure you can find it. Hit enter, and make sure you're getting the same thing that I get. So before you go ahead and pause the video, try that out, and make sure that you're getting this as an answer before you move on. Okay, so then if you wanted to do it manually, and I don't know anybody that wants to do this, but it is possible to do it without this, you could say, well, I've got 60 degrees, and then to know the number of minutes, you could say, well, let me try 20 minutes, let me try 25 minutes, let me try 28 minutes, let me try 32 minutes, let me try 33 minutes. And at some point, your decimal ends up being too big, and then you have to walk it back. So then you say, okay, well, 32 minutes. And then you do the same thing with seconds. You might try 20 seconds and see that it's not quite enough, and 22, and 24, and then 25. And then you realize 25 is a little bit too much, so you walk it back one to get to 24. So it's a lot of guess and check, not very mathematical, but technically you don't have to have the calculator's function to do that. So feel free, if you want to try that out, go for it. It's not something I'm really going to refer to very much. Alright, and to finish off with some of the foundation stuff, you need to be familiar with the term called arc length. You need to know what it is and how to work with it in our new formula and with radians. So back in geometry you learned about circumference, and circumference is the total length around a circle. Circumference is 2 pi r, by the way. You should probably know that for the ACT. Arc length is just part of the length around the circle. So again, if I wanted to know all the way around its perimeter, but if I only wanted to know part of the way around, that's arc length. So one way to find arc length is with this formula, and you should memorize that. And then this formula, S represents arc length, R represents the length of the radius, and theta, this little Greek symbol, is the measure of the central angle in radians. I put that in bold. Okay, so here's circumference. Alright, so if we compare these two, it's like circumference is all the way around, So, well, how many radians is all the way around a circle? 2 pi. So they're just, that circumference formula that used in geometry, they substituted 2 pi in for you. R is still R, all the way around the circumference, whereas part of the way would just be arc length. But if we just went halfway around, we would just put pi. That's the only difference. So it's really just a variation of the formula you already know. So let's sketch a circle with a radius length of 2 inches. Find the arc length of an arc with a 45-degree central angle. So 45. Central angle means right here at the center. And so this question is figure out how long is that piece right there. If I was to straighten that piece out, how many inches would that be? Alright, well, S equals r theta. S is the arc length. And you might be tempted to say 90, but the units are inches. But think about that. This is 2 inches, and that's 90 inches. Those numbers don't seem like they're in the same ballpark to me. And it comes back to this. It's an easy formula to use, but your theta has to be in radians. Has to be. So you have to sidebar and say, wait, well, 45 degrees, we would convert it like we did earlier. You see 45 goes into 180 4 times. Now again, once you know the unit circle, that's a lot quicker. So you don't want to put 45 there, you want to put pi over 4. So you multiply these, you get pi over 2. And so then that's your answer. Half of a pi would be the length of that. Now, if you were told to round, again, you really shouldn't round unless you're forced to. But if I round that in my calculator, it's about 1.571. And that makes a lot more sense. If this is 2 inches, this being about 1.5 is a lot closer. 90 should not make sense though. Okay, let's do another one. Let's find the measure of the central angle of a circle that has this radius and this arc length. Okay, so the radius is 75 feet, and the arc length I want is 60 feet. What would be the measure of the central angle? Well, this formula still applies to us because we know 2 of its 3 variables. So S equals r theta. So 60 feet equals 75 feet times theta. Divide both sides by 75 feet. And then let's reduce this. Let's see, if I divided this by 5, this would be 12. The feet are going to cancel. And if I did this by 5, 15. And then these both divide by 3. So it looks like 4/5. I'm checking with my calculator here. Yes. 4/5. Okay, but this is an angle. So is it 4/5 degrees? Is it 4/5 radians? Well, that's why I kept up with the feet units for you. When I divided 60 feet by 75 feet, the units went away. And remember, when the units go away or you don't have units, it's understood to be radians. So 4/5 degrees is incorrect. 4/5 radians is fine. Alright, so some of these arc length you will use a little bit less throughout the year, but converting between these is an ongoing thing. Complementary and supplementary is pretty common. Coterminal angles comes up all year. Converting between degrees and radians and vice versa comes up quite a bit. So all of these things are kind of your foundation, some of your building blocks to use on other trig topics as we get to them. Alright, so that's all I've got for this video. You should be ready to practice a little bit of all of these and see where you struggle, and then we will go from there.